Welcome to Lesson 7D, Temperature Inversion, Absorbing Ground, Part 2. Last time we did two cases with ground-based temperature inversions. We did these for absorbing ground. Now we're going to continue the absorbing ground and temperature inversion, but instead of ground-based, case 3 will be an elevated temperature inversion. We'll still have an absorbing ground with the stack below the bottom of the inversion. So let's define it this way. We're going to define HT as the distance from the ground to the bottom of the elevated temperature inversion. This is the inversion. Notice that it's above the ground. There's some unstable region in here up to the bottom of the temperature inversion, and then it's stable above that. It could go unstable later, but actually it doesn't matter what happens up here. We don't really care at all what happens up here, because when the plume hits the bottom of it, it's trapped, it reflects off of that, and it stays flat on top. So we don't really care what happens up there. Inside the plume, though, since the stack height H is less than HT, as we see here, we know that this plume is going to hit the temperature inversion, and then it will stay flat, and it will also keep going down till it hits the ground. So we call this a fumigating plume. This is a bad case where people down here will experience and breathe that air pollution. Now, it doesn't really matter if the top of the plume hits this inversion first or it hits the ground first. In either way, this is going to reflect and cause this concentration here to be more concentrated, the higher level of air pollution, because of the lid up there. This is an absorbing ground, so anything that happens under the ground we ignore. So this part of the plume is kind of lost. It disappears. We don't worry about it anymore. Inside here, unlike the previous examples, these two, the plume was inside the temperature inversion, so these were class F for the temperature inversion, the most stable case. Here, it could be any class A, B, C, D. It really shouldn't be E or F because those are stable, but there's nothing to prevent us from having these classes and then have a temperature inversion that's up above. And there are conditions that cause that I'm not going to get into it. I'm not an expert in meteorology. But notice here also HT is defined as the bottom of the elevated temperature inversion, where it used to be the top when we had a ground base. So keep this notation in mind. So the question is, how do we modify this Gaussian plume? Well, this acts like a reflection, so we can say that the bottom of the elevated temperature inversion at this height here, it's acting like when we did a reflection off the ground. Remember when we talked about a reflecting ground, we said the plume will come in and reflect off the ground. Well, here it's an absorbing ground, so we don't have that going on, but we do have a similar kind of reflection going on up here. So if you remember before when we talked about a reflecting ground, we added an image source under the ground. So we put an image source down here at the same distance H from the ground up as it is from the ground down below the ground. We put that image source. Well, now we don't need that image source because it's not a reflecting ground. But we do need an image source up here to account for the reflection of this lid. I like to call this a lid. It's like a ground up in the sky that just reflects. So we'd add an image source there, just like we used to do down here with the reflecting ground. So then the question becomes, what height should this be? What should be the elevation, the Z location of this image source? So we have to do a little bit of geometry there. By the way, since we're mirror imaging across this inversion, we don't care what's going on up here. This temperature effect is not part of the new plume, the image plume we added. We're just mirror imaging everything below that bottom of that temperature inversion. So we still see this up here, just a mirror image of everything. So in other words, this image source is identical to the real source. And then the question is, where do we put it? And the answer is, to make a proper image source, you have to have these two distances that I circled to be equal to each other. And then you'll have a reflection across the lid, which is the way I drew it here. How do we figure out what that is? Well, it's just a little bit of geometry, and I'll do a quick example problem to consider that. Let's take a stack that's height 50 meters and has buoyancy of 20. So we know that H is equal to 70 meters. And then let's suppose that HT is 95 meters. So HT, remember, is this height from the ground to this bottom of the elevated temperature inversion. We need to know what's the location of this image source. We'll call that ZI. This is the real source, ZR. That's at H. Remember, Z goes up from the ground. So the real image is at H, and then this is HT. So let's calculate the elevation above the ground where we need to place this image source. Let me just re-sketch this to make it a little more clear for the geometry that we're about to do. What we need to do is make this distance equal to this distance. And this distance here, you can see just is HT minus H. So let's make this distance also HT minus H. So what is ZI then? ZI, you can tell just from adding up these heights here. ZI is HT from here plus HT minus H from here, and that gives us 2HT minus H. So that's our answer in variable form. And then in this particular problem, I gave some numbers. So in this case, ZI or Z image is equal to 2 times 95 meters. That's the HT minus H, which was 70 meters, and this turns out to be 120 meters. So that's where you would put the image source in this particular problem, and that would give you an exact reflection about the bottom of the elevated temperature inversion, which is exactly what we want. So we can summarize this into an equation.
Hey, Professor, look at me. I can be an image source too.
Thank you, Joe, for that insightful comment. Problems are getting more complicated in a sense, but in another sense, they're getting easier because we've seen this over and over again. We're going to use this mathematical identity again, and we're adding just an image source at 2HT minus H. And if you remember, when we did an image source for the reflecting ground, all we did was take this term Z minus H squared within the exponent and add another one with Z plus capital H. So we had a Z minus H term and a Z plus H term because that was a reflection directly off the ground. Now we do the same idea, except instead of we have our original source and then we add, instead of Z plus H, it's Z, because that one was a Z minus a negative H, recall. Then this is Z minus the image location, which is 2H minus H. So we just take Z minus 2HT minus H and then put that in the equation as another term. So what have we done? We have the real source here, and then we have the image source here. And I've already done this math for you to make it easier so I don't have to keep writing out. This term is common to all of the real sources and image sources. All of the sources have that part with it. And then this group of constants is the same for all of them. So this is our equation, and I have it labeled here. So it's a Gaussian plume model for an absorbing ground with an elevated temperature inversion, where the bottom of the inversion is at Z equal HT, and we have to have HT greater than H. Otherwise, if the plume were up higher, if the plume were way up here somewhere above the bottom of the temperature inversion, then you would not ever get to the ground because it would be blocked, as we already talked about. So we're talking about a case where HT is greater than H, and we added this image source. How do you do this? Well, for a given location, X, Y, Z, you can easily solve for CJ at any location of interest. So that's one thing we need to do. But it's more interesting to look at the hazardous area. So let's do an example problem. I'm using, again, exactly the same numbers that I did before. So this is the same problem, just changing something a little bit here. The same chemical plant emitting a gaseous air pollutant. And here's the stack height. So this is all the same as before. HS, we had our delta H. We can get our capital H, which was 100 meters. And then we have our average wind speed of 5.0 meters per second. Our m dot JS is the same as before, 110 kilogram per second. It's an overcast morning. And even though there's a temperature inversion, I said always use class F for a temperature inversion. That's when the plume is inside the temperature inversion. Here, it's under the temperature inversion. We have an elevated temperature inversion up here. Here's our temperature inversion. And then its temperature looks something like that there. The stack here is lower than the temperature inversion, as I said. This temperature inversion extends up to 125 meters. So that would be our HT is 125 meters to the bottom of the temperature inversion. The ground absorbs the air pollutant, and the PEL is still 50, is the same as before. We're even using the same X so we could compare directly. So at 4.85 kilometers downwind of the stack and at ground level, we estimate the horizontal extent of the hazardous zone in the Y direction. I'll actually plot it like I've been doing, and we'll compare to what we had got previously. So it's the same problem. The only difference is that we now have a elevated temperature inversion in this problem. So if I had asked you for CJ at some X, Y, and Z value, I give you the X here. If I gave you some Y and some Z, maybe ground level or some breathing height here at this point at some X and some Y on the center line or Y off the center line, you basically just plug into this equation directly and you have your answer. So that's easy. The harder part is to find the hazardous zone or hazardous area. Sometimes I call it area, sometimes I call it zone. I guess the difference is zone would be a volume and area would be just an area. So I probably should use area there to be more technically correct. And we're going to do this one at ground level, so z equals 0. So how do we solve this? Well, we've done this several times now, so this is getting to be old hat. First, we set Cj equal PEL here, because we want to find the location y. This is our unknown. We want to find y where Cj is equal to PEL. That'll be the outline of our hazardous area. Then we solve for y. And we know everything else. We know HT, H, we know that we can calculate the sigmas at a given X, so we're given an X. We know everything here except Y, and you solve for Y. This looks like an ugly equation, but you're getting used to this by now. And if you do that, and I would encourage you strongly to do that, and I'm not going to give you the answer again because I want you to work on this, but you've done this many times, you'll get the same form of the answer, y equals plus or minus sigma y times the square root of -2 natural log of a bunch of stuff that includes these exponents and things. It's really just a couple lines since I already did the mathematical manipulation using this rule that we had up here, which is a key to solving for y. That allows us to isolate y, and then we get the final equation. So that's our answer in equation form. And for this particular problem, make sure you can get these answers with my numbers. So I get y equal plus or minus to 3 digits, 346 meters at our x of 4.85 kilometers. So that's our answer. And that's the extent of the hazardous area. Remember on the quizzes, if I ask a problem like this, I will just ask for the half width. So you would give 346. We don't worry about the plus or minus. So as I've done before, I will repeat this for many different X locations and plot the hazardous area. And I used Excel, which I find very convenient for doing these kinds of things. And I see now my legend got cut off at the top a little bit, but you can still read it. Sorry about that. Actually, for comparison, I also compared to the same case, but without the elevated temperature inversion, which we had previously. Before we added any temperature inversion, we just had an absorbing ground. That's the blue one. The blue one is the case with no temperature inversion, and it's a class D, so they're both class D. And this is what we get now with the elevated temperature inversion. And so you can see it looks like an egg within an egg. And the distance here, if you remember from previously, at 4.85. So we're doing all this work at 4.85 kilometers as an example. So that's right before 5 there. If you come up and plot these things, you can see it is almost exactly at 250. If you recall, for the case without any temperature inversion, this was 250 meters. And now for our case, from 0 at this same X location up to here, this distance turns out to be 346 meters, which is the value that I wrote up here. And it's symmetric in Y along the Y axis or across the Y axis. A couple comments about this analysis and this result, which are kind of interesting. The hazardous area now is much larger than previously, and so some numbers. We had this extent before for the blue case, the previous case, the extent was 1.5 to 7.5 roughly kilometers, and now here it's 1.5 to about 12.5 kilometers. My second point will be for us to look at this region near the front or the closest to the plume on the ground. Near the front, near the nose of the hazardous area, I'll call that the nose, these are identical. You can see that they overlap each other. So what happens is that the real source hits the ground first, so that if we go back to our sketch, the real source hits the ground at roughly, in this case, about 1.5 kilometers, and then the image source doesn't hit the ground till much later. So there's a region where the two comparison of with and without this temperature inversion look identical for a while until that second plume, that image source, hits the ground. So that's why that green area and the nose looks the same either way. So this area here is the same in the blue and the red. So that's what I mean. It's identical near the nose. But then you start to see the effect of the image source. And that's why hazardous area gets bigger when you go further downstream, because you're seeing the effect of the source, the real source, and the image source. So in this purple region, then the image source starts to affect CJ near the ground, and then you start to see this hazardous area grow. So my formal comment here is that the temperature inversion concentrates the air pollutant under the inversion due to this reflection in the sky, just like it did before when we had a reflection on the ground. Now we have a reflection in the sky. Another comment, this fumigating plume is the worst case scenario for an absorbing ground, but it would be even worse for a reflecting ground, and we'll talk about reflecting ground in the next lesson. One final comment is that I think this is pretty cool that we can do this kind of analysis. And like I said before, even though it seems to be getting harder, we're adding these reflections and images and stuff. The algebra isn't that much harder, because if you've been following my advice and you have this already coded up in your Excel or MATLAB or whatever you're using, it's very easy to change. Just change some of the equations a little bit and you can run it again. So that's hopefully what you're doing for the quizzes, for the homework, and you should have no problem. And so that's where I will stop.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.